All right, so let's talk about something fascinating. We're going to look at one of the most basic, most common electronic parts out there. I mean, this thing is in pretty much every single device you own. But here's the crazy part. Hidden inside its super simple job is a secret, the potential for pure, unpredictable chaos. So, could your computer's most common safety switch, the thing meant to protect it, actually be the thing that causes it to crash? It sounds totally backwards, doesn't it? A component designed to save your circuits from, say, static discharge, having the power to throw them into complete chaos? Well, you guessed it, the answer is a surprising yes. It absolutely can. And the answer to how this all works lies hidden inside a circuit that looks, well, incredibly simple. Seriously, you look at this and you see a power source, a few wires, and the star of our show today, a tiny little component called a diode. Okay, so to really get how chaos can just bubble up out of a perfectly normal system, we've got to get to know our main character here, the diode. And this is where things start to get really interesting, because that simple little switch, it's not nearly as simple as it looks. So if we lived in a perfect textbook world, a diode is basically just a one-way valve for electricity. Think of it like a one-way street, right? Current can flow forward, no problem. But if it tries to turn around and go in reverse, nope, the gate slams shut. Super simple, super reliable, and totally essential for keeping electricity flowing where it's supposed to.
But here's the thing. We don't live in that perfect textbook world. And our electronics, they aren't built with ideal parts. Real diodes, the ones actually in your phone or computer, have these tiny physical flaws. And it turns out, these little imperfections aren't just minor glitches. They're the secret ingredients we need to unlock chaos.
Let's talk about flaw number one. It's called reverse recovery time. So when that one-way valve is supposed to slam shut, it doesn't happen in a snap. There's this tiny, tiny delay before it actually closes all the way. It's almost like it hesitates for a split second before doing its job. And then there's flaw number two, parasitic capacitance. It sounds complicated, but here's the deal. Just because of how it's built, every single diode accidentally stores a little bit of electrical charge. It acts like a teeny, tiny battery that it was never meant to be. It's not a design choice, it's just physics, an unavoidable side effect. So, what you're seeing here is a classic don't judge a book by its cover situation. On one side, you have the super simple symbol that an engineer draws on a schematic. But on the other side, that's what's really going on under the hood. It's a switch, sure, but with all those little built-in flaws we just talked about. This perfectly shows the hidden complexity that we're about to play with.
Okay, so we have these flawed components. How do you get from a tiny flaw to full-blown chaos? Well, a group of researchers at the University of Maryland started wondering, what if we could take these flaws and instead of trying to fix them, we deliberately push them to their limit? They actually came up with a 4-step recipe to do exactly that.
Step 1, you grab one of our imperfect, real-world diodes, flaws and all. Step 2, you hook it up to a special kind of cable, a transmission line, that basically creates an electrical echo. Step 3, you mess with the wiring on purpose to create a mismatch, which makes that echo bounce back and forth, like a hall of mirrors. And finally, step 4, you just crank up the power. And this is what that recipe looks like as a real circuit. You've got your power source pushing everything along. You have that transmission line acting as a kind of echo chamber. And right at the very end, there's our flawed little diode. Now what happens is, the electrical waves start bouncing back and forth in that echo chamber, and they start interacting with the diode's delayed reaction time, and that's when things get really weird. So here is the crucial insight, the real aha moment of this whole thing. The researchers figured out that chaos doesn't just pop up out of nowhere. It emerges when 3 very specific timescales in the circuit all line up and are roughly the same. It's like you have 3 different clocks, and when their ticking suddenly falls into this strange, unpredictable rhythm together, boom, chaos. So what are these 3 clocks? Well, first you've got the diode's own hesitation time, that reverse recovery we talked about. Second, there's the travel time for that electrical echo to go down the wire and back again. And third, you have the rhythm of the power source itself, the time between each electrical pulse you're sending in. When those 3 timings get into the same ballpark, the whole system just goes haywire. All right, so the theory sounds solid, right? The recipe is all laid out, but the million-dollar question is, did it actually work? Could they do this for real? This is where it gets really, really cool. Now, to actually see chaos happening, scientists use this amazing tool called a bifurcation diagram. It's basically a map that shows you the road to chaos. As you slowly turn up the power,
a single, stable signal will suddenly split into two possible states. Turn it up more, and it splits into 4, then 8, until suddenly it just explodes into this fuzzy, unpredictable cloud of possibilities. That cloud, that's the unmistakable signature of chaos.
And here it is. This is the smoking gun. On the left, that's what the computer model predicted would happen. It's the theory. And on the right, that's what they actually measured from the real-life circuit they built. Just look at that. The similarity is absolutely incredible. It's almost a perfect match. The experiment didn't just support the theory, it nailed it.
Of course, being scientists, they put it a little more modestly. They said the comparisons were in general agreement. That's some serious scientific understatement right there. Because what this really was the moment they proved, without a doubt, that this simple little circuit could be turned into a reliable chaos generator. And get this, they weren't just doing this at some slow laboratory speed. They managed to create and watch this chaos happening at over 1.1 gigahertz. To put that in perspective, that's right in the same ballpark as the speeds modern computer chips and Wi-Fi systems run at. So this isn't just some weird theoretical curiosity. It's happening at speeds that are incredibly relevant to the technology we use every day. So, okay, we found chaos hiding in plain sight inside a simple little switch. What's the big deal? Why does this matter? Well, it turns out this discovery is kind of a double-edged sword. It's both a pretty serious warning and a really exciting new opportunity. On one hand, you have the danger. Those very same diodes that are put on motherboards to protect them from static shock could, if the conditions are just right, start generating this chaos and cause unpredictable errors, or even crash your whole system. That's the scary part. But then there's the opportunity. Because this chaos looks just like random noise, we could potentially use it as a kind of digital camouflage. We could hide encrypted data inside it, creating super secure, high-speed ways to communicate that are almost impossible to eavesdrop on. And that leaves us with a really fascinating question to think about. Is this hidden chaos just a bug? A dangerous flaw that engineers need to stamp out and design around? Or is it actually a feature? An untapped power source just waiting to be harnessed for the next wave of technology? You know, the answer's probably a little bit of both.